Nomenclature of carboxylic acids. Carboxylic acids has a functional group named carboxyl. Carboxyl is C double bond O. That carbon is attached to OH. So this is functional group carboxyl. Given is the structural formulae, IUPAC name and common name. For carboxylic acid with one carbon is called metanoic acid. The common name is formic acid. 2-carbon carboxylic acid, ethanoic acid, IUPAC name, and the common name is acetic acid. For 3-carbon carboxylic acid, the IUPAC name is propanoic acid, common name is propionic acid. And 4-carbon butanoic acid, butyric acid, and so on. So you have to memorize the common name and IUPAC name in order for you to draw the correct structural formula. In naming the carboxylic acid, we start with selecting the longest continuous carbon chain that has carboxyl group, and the carboxyl carbon atom is numbered as carbon 1, but omit this number from the name. For example, we have here 1, 2, 3, 4, 5, 6. Longest carbon chain 6. So it doesn't matter whether it is straight or bent. You have to find the longest carbon chain that contains COOH. Include this carbon. And then the COOH must be numbered as carbon 1. But omit this number from the name. The parent name is hexanoic acid. Don't include 1 here, omit this number, so you don't put 1 hexanoic acid even though the COOH is at carbon 1, we ignore that number 1. So the parent name is just hexanoic acid. And then the final E in the alkane is replaced by suffix oic acid. So carboxylic acid name is the only name that you have to put space. We don't put space in naming except for carboxylic acid. You put space, oic space acid. And then at here, carbon number 5, you have hydroxyl group. So the name of this compound is 5-hydroxyhexanoic acid. If there are 2 COOH groups, the compound will be named as alkane dioic acid. Di means 2 COOH. For example, pentane dioic acid. Okay, here 1 carboxyl group, 2 carboxyl group, dioic acid. An aromatic dicarboxylic acid, the COOH, 2 COOH at the aromatic ring is named as 1X. X is the position of another carboxylic acid, another carboxyl group. 1X benzene dicarboxylic acid. For example, here carbon 1 and then at carbon 3. So 1,3 benzene dicarboxylic acid. Okay, it's applicable for aromatic carboxylic acid. A cyclic carboxylic acid is named as cycloalkane carboxylic acid. For example, here cyclic carboxylic acid, cyclic ring attached to COOH, so the name is cyclohexane carboxylic acid. Hexane because 6 carbon in this cyclic ring, so cyclohexane carboxylic acid. And this must be number 1. In cyclic and aromatic, carbon 1 is this carbon, not the COOH carbon. In straight chain, C double bond O is carbon 1. But in cyclic ring or aromatic ring, the carbon that is attached to COOH, that carbon is carbon 1. So since this is carbon 1, methyl carbon 2, bromo carbon 4. So the name is 4-bromo-2-methyl cyclohexane carboxylic acid. When a compound contains a carboxyl group and other functional groups, the priority given to the carboxylic acid as the parent name. So here we have alkene and carboxylic acid. Refer priority table. The carboxylic acid has higher priority than alkene, so carboxylic acid becomes the parent. So the name of this compound is 3-methyl-2-cyclohexene. Double bond hexene 2 means the double bond is at carbon 2, 3 methyl, substituent methyl at carbon 3, carboxylic acid. Physical properties of carboxylic acid. There are 4 factors that affect the boiling point. The first one is number of OH group, followed by molecular size, and then polarity. Finally, effect of branching. This is only used when the number of carbons are the same. Then we can explain about branching. Boiling point of carboxylic acid is higher than alcohol, ketones or aldehydes of similar molecular size. We know that carboxylic acid, alcohol, ketones, aldehyde, they are all polar compounds. But the carboxylic acid has higher boiling point than those three because carboxylic acid exists as stable dimers through hydrogen bonds. Molecules in dimers are arranged closely packed. Only carboxylic acid molecule arranged closely packed. Not alcohol, not ketone, not aldehyde. Only carboxylic acid arranged closely packed due to the stable dimers through hydrogen bond. We're going to look at how dimers form. Therefore, the hydrogen bonds in carboxylic acids are relatively strong. Due to the dimers, alcohol, ketones, aldehydes do not have the stable dimer. Only carboxylic acid has. Higher energy is needed to overcome the intermolecular forces between the carboxylic acid. So this is the stable dimer, dimerization of carboxylic acid. This green molecule, one molecule of carboxylic acid in green and another one molecule of carboxylic acid in blue. So in order to form hydrogen bond, the C double bond O, this oxygen of C double bond O form hydrogen bond with hydrogen of OH of another carboxylic acid. Same goes to this one. And if you look at here, this dimerization, it is arranged in a proper manner. So when it is arranged in proper manner, it can arrange closely packed together. But not in alcohol. Only in carboxylic acid the arrangement is like this. So this proper manner arrangement causes molecule arranged closely packed. When it's arranged like that, the hydrogen bonds in carboxylic acid are stronger than alcohol. So this is the dimerization of carboxylic acid. The boiling point of carboxylic acid is higher than alcohol because carboxylic acid forms stronger hydrogen bond. The C double bond O in carboxylic acid add electron withdrawing group, which causes OH group in carboxylic acid to be more polarized than the OH group in alcohol. So here the hydrogen bond in alcohol, this is how hydrogen bond between alcohol molecules are formed. So if you look at here, this hydrogen bond, it's not arranged closely packed. It doesn't have pattern like the one in carboxylic acid. So alcohol molecules cannot be arranged closely packed because it's not in proper manner. So carboxylic acid C double bond O at electron withdrawing group causes OH group in carboxylic acid more polarized. Means this is delta minus, this is delta minus, so it attracts electron towards itself, making this more delta plus, this one more delta minus. So in the carboxylic acid, it is more polarized. But in alcohol, only delta minus and delta plus. There is no one more oxygen like the carboxylic acid. Carboxylic acid, you have two delta minus which attract the electron towards the oxygen, which it makes more polarized in carboxylic acid. Next, we're looking at solubility of carboxylic acid in water. When we talk about solubility, we are talking about solubility in water or in organic solvent. We are looking at the bond forming. Solubility is about bond forming. Boiling point is about bond breaking. Now, carboxylic acid are soluble in water because it can form hydrogen bond with water. Carboxylic acid can form hydrogen bond with water. So that's why carboxylic acid are soluble in water. The solubility is about the same as alcohol with the same carbon number. But for carboxylic acid, as the number of carbon atom increase, the solubility in water decreases because we know that the carbon chain is the hydrophobic portion. Okay, carbon chain is the hydrophobic portion. Carbon doesn't like water, hydrophobic portion. When the bigger the hydrophobic portion is, the less soluble it is in water. Carboxylic acid, which has less than or equal to 5, are water soluble because they can form hydrogen bond with water molecule. But carboxylic acid having more than 5, 6 and above are water insoluble. Even though it has COOH, but it is insoluble due to the long carbon-carbon chain, the long non-polar alkyl portion. Okay, so that's why 6 and above carbon insoluble because you have bigger hydrophobic area. Hydrophobic area is insoluble in water. Aromatic carboxylic acid, aromatic, the carboxylic acid which has benzene ring, means you have 6 carbon in total. Look at here, more than 6, water insoluble. But here aromatic carboxylic acid are slightly soluble, slightly, not completely, it's just slightly a bit soluble because it's 6 carbon. It's unlikely to be soluble, but aromatic carboxylic acid are slightly soluble due to the huge aromatic ring. The total of carbons are 6. Dicarboxylic acid can form more hydrogen bond because you have 2 COOH. So dicarboxylic acid more soluble since more hydrogen bonds can be formed. Now we are looking at the solubility of carboxylic acid in non-polar solvent. Non-polar solvent, we are forming the van der Waals forces between non-polar solvent and the hydrophobic area of carboxylic acid. So, carboxylic acids are soluble in non-polar solvent, such as benzene. So here the example of non-polar solvent is benzene. So when you put carboxylic acid in benzene, it is soluble because the carbon part in the carboxylic acid can form van der Waals forces with the benzene solvent. So here carboxylic acid R, the carbon part, it can form van der Waals forces with the non-polar solvent benzene, which makes the carboxylic acid soluble in non-polar solvent. Okay, so when we are talking about solubility, it's about forming the bond, forming the forces. So here, hydrogen bond only exists between the molecule. It has hydrogen bond, but only exists between the carboxylic acid and another carboxylic acid. Solubility in non-polar solvent, we're looking at whether it can form bond with the benzene.